Dear ladies and gentlemen, welcome to the first webinar in 2021. So the topic today is plastic gears. As you may have heard or maybe seen, last year we already held a webinar on plastic gears. It was held by Dr. Pogacnik, and we have received a lot of feedback from you and from other users of KISSsoft that people would like to see more some practical cases how plastic gears are really calculated inside KISSsoft. So in this webinar, we will stick not so much to the theory, which was presented last year already, but show you more the handling of plastic gears in KISSsoft. My name is Ilja Tsikur. I'm working in sales, and the webinar today will be held by Mr. Hanspeter Dinner, our Director, Global Sales. Just two more short remarks. You will find the PPT, the PowerPoint presentation, directly available for download in the tool. And of course, we would appreciate if you would ask questions either during or after the webinar so that we can answer some of them at the end of the session. So with these words, I am finished. And Hanspeter, the stage is all yours.
Good morning or afternoon, ladies and gentlemen. My pleasure to meet you. At least you can see me. My name is Hanspeter Dinner. I'm responsible for our global sales operations. My background is in mechanical engineering. I started studying structural statics and biomedical engineering, then went into finite element calculations. And about 18 years ago, I joined KISSsoft company. In between, I was working as a gear consultant for about 12 years. Today, we look on a few aspects of plastic gear design. The presentation will be structured in 3 parts. The first part is slide-based, just a few slides to get us started. Then the majority, the bulk of the time, will spend inside KISSsoft software. I will work through an example. In this example, again, we have 3 steps that we will look into, and we will finish off again with a few slides, those slides giving hints at additional resources and capacities on our side. Let us start with the reason why we run calculations. The reason is to prevent failures. Still, they will happen. For plastic gears, the failure modes are very different, or the typical most prominent failure modes are very different to those for metallic gears. Many of them are related to wear phenomenon and temperature and the unique material properties of, in particular, thermoplastic gears. In the top left corner, you see what happens if there's too much friction. For example, if there's no lubricant and a lot of power being transmitted, then it may happen that due to the friction between the mating flanks that are in direct contact, the teeth heat up and eventually fail as a thermal failure. In particular for thermoplastics, they simply melt. In the top right corner, the classical crack that progresses through the root of a teeth is not that often, not that a common failure mode in plastic gear. It's in particular there for thermoplastics with a high crystallinity grade, for example, PEEK, under high load. More common, however, in the bottom right corner are deformations due to overload. That can happen, for example, if there are elevated temperatures or if it is a flap closing mechanism so that torque remains applied even when the gear is not rotating anymore. This is the case when the motor, the electromotor, for example, acts as a brake to close, for example, a flap. Then the material may creep, and then there may be a permanent deformation. Today we look at the failure mode in the bottom left corner. That's wear. means material is removed progressively from the flank, thereby weakening the tooth, leading to later on a failure mode that can be deformation because the cross-section is too small, or that the tooth simply breaks off. See top right corner. Wear is one of the most common and most feared failure modes in plastic gears. The main difficulty is that the wear is a matter of the material pairing. It is not only a matter of, it is not only influenced by the material of the gear that is of interest, but it is also influenced by the material of the mating gear and even the type of lubricant. If there's contamination of the lubricant, then it is as a fourth component, of course, depending on the contamination. The images you see here are taken from this PhD thesis. One issue that we experience, and also those people we talk to, is that there are very few public resources, means books, for example, specifically on plastic gears that go to a certain level of depth. Frankly, I do not know a single good book on plastic gear design and analysis. The best one I have ever seen, I found it in China. It contains some of our material, of course, not having asked for permission. And what we most often do is that we refer to PhD theses, in particular in Germany, of course. We believe there are three main areas where plastic gears are a matter of research. First and foremost in Germany, then in Japan and in the US. And we typically advise to go directly to those research bodies and look at the PhD theses generated there. Now, wear, how do we calculate the amount of wear? Let me just explain the basics of the formula. If the wear amount is a function basically of 4 parameters. That is the specific wear rate. That's a material property, means a property of the materials, means material gear 1, material gear 2, the lubricant and possibly contamination thereof. Then the contact pressure between the flank. The contact pressure can be calculated by formulas from gear standards or by a loaded tooth contact analysis. In the presentation today, we will look at the loaded tooth contact analysis, means a very detailed and local contact pressure distribution calculation. Then we have the sliding speed between the two flanks. The more sliding speed we have in over a certain amount of time, the more total travel we will experience. Therefore, the wear volume will increase. And then, of course, everything is a function of time, or time can also be expressed as a number of rotations of the gears in mesh. These are the 4 parameters. Today, we look mainly at the load distribution and the effect thereof, because the material parameter is something that is out of control with respect to the software. It's depending on your choice of materials and lubricant. Also, it is often not known, and that's one of the main issues. You don't know this parameter. You have to assume something, tinker with it, optimize the gears, see how they improve, but it's very difficult to rely on absolute values of the wear, because the absolute value of the wear or the specific wear rate is not known exactly. The speed at which the flanks travel on each other, that's very well known from gear theory, from the geometry, and how long you operate is a simple input. So the 2 things that are really of concern are the material properties that are difficult to figure out and not a matter of the software, and the true contact pressure distribution, that is very much a matter of software from the loaded tooth contact analysis. Then I have to explain that in the software we have two approaches for calculating the wear. We have a non-iterative calculation here on the left side and an iterative calculation here on the right side. Let us start with the left side, with the non-iterative calculation. What we do is we start with the original tooth form. That is the black line, like an involute. It may contain modifications. Then what we do is we run a loaded tooth contact analysis, means we calculate the true stress distribution on the whole flank. Once we know the true stress distribution on the whole flank, of course, we also know the sliding speed depending on the position of the on the flank, or rather as a function of the diameter. And from the sliding speed, the contact pressure, and this wear rate, the specific wear rate, the material property, we can calculate how much wear results. From this calculation, we find then the green line. That is the tooth shape after wear. What you can see here is that most of the wear, and it's of course too much for a realistic example, but for the sake of the presentation, I had to make it very clear. What we see is that at the start of mesh, this shape here representing the driving pinion, means the driver. At the start of mesh, which is then in the dedendum area of the driver, we have a high contact force at the start of mesh when the pinion engages with the tip area of the gear. So we have a high contact pressure, and of course at the start of mesh we have a high sliding speed in the direction of the tooth form. Since then both parameters, contact pressure and speed, are high, the resulting wear is highest down here. Around the pitch point, the wear is near zero because there is no sliding. Gears are rolling only. Therefore, theoretically, there's no wear. And on the tip side, there is less wear. But this is not true. It doesn't comply with experience, this shape. The reason is, once some material is removed in this area, then at the start of mesh, this high pressure is relieved. Means the initial wear acts like a root relief. Then the wear is reduced. To accommodate or to consider this effect, we have the iterative wear calculation here on the right side. This means in a first calculation, we calculate the true stress distribution on the original tooth form and allow some wear, just a few microns, for example 10 microns. We calculate a new gear geometry after, for example, 10 microns of wear, and then recalculate the contact pressure distribution, now considering that the flank is not of the original shape anymore. And since down here, material has been removed, in the next calculation, the contact pressure down here will also be reduced because we have like root relief applied. So the result of the previous calculation, the tooth form after some initial wear, is considered for a recalculation of the contact stress. And then again, we remove some material, recalculate the contact stress again, multiply it with the sliding speed, remove some material, and so on. And then you can see a number of lines, each line representing a tooth shape after a certain time, after a certain amount of wear. With this, we find a much more realistic final tooth shape that complies very well with practical experience in the field. We also find some wear at the pitch point, which is also in line with field experience. Here, that theoretically there's nowhere around the pitch point, that is contradicting field experience. In the course of today's presentation, I will always use this iterative where calculation that gives far superior results. Now enough slides, let us move to the software operation. I have prepared here an example. We see this gear in mesh. The blue color is the driving pinion. The green color is the driven gear. You can already see that the blue color pinion has some undercut. It's not really a nice design. This design is from an actual project where the customer had an original gear design and he experienced some failures in the field. And he approached us asking, how can we optimize the gears without changing the overall size significantly? So typical question, improve it, but don't touch anything. So here we see the mesh, here we see the specific sliding, and in the bottom left, we see a single tooth of the pinion in greater detail. You can already see from the specific sliding that at the start of mesh, we have a very high negative value. This means down here on the pinion, we will have a high sliding speed, resulting in a lot of wear. Now let me run the wear calculation. The wear calculation in KISSsoft is part of the contact analysis. In the contact analysis, I can define settings, how to consider the load data, settings on how many steps to do in the load distribution calculation. And for the iterative wear calculation, I can define what is the maximum amount of wear that is considered in one iteration. Means here the steps from calculation to calculation is not more than 10 microns of wear. And I tell the software if it takes more time than 50 calculations, stop. I now execute the calculation by pressing the F5 button on the keyboard. And now you can see these messages popping up and you can see the messages repeating themselves. These are the iterations. You can see counts up, one calculation is finished, the next calculation step starts. We now find that the flank, the original flank being this black line, the flank has deteriorated, it has worn, and the shape of the tooth after 400 hours of operation, I entered to the software that the operational time is 400 hours. This is now the shape of the flank after these 400 hours. And here, approximately here, we have the highest amount of wear. If I measure this, we find approximately 0.135 millimeter or around 130, 140 microns of wear. This number, this amount, is of course shown in the results table down here, and the true value or the calculated value is at 137 micron. And the iteration that leads to this result is shown in a second graphic. You can see each line here shows a status of the tooth after 7 hours, 14 hours, 27 hours, and so on. And finally, after 400 hours, we find this final geometry And this final geometry, this line in cyan color, is the same line as here in red color. Or let me change the color code here as well. So these are the same lines, the same graphic. The difference is here on this graphic, I see the intermediate steps as the wear progresses. So this is how we run a calculation. We now find that the highest amount of wear, the depth of wear, is 137 microns. We now want to improve, means reduce this value. Let me put the graphics aside. And the first thing that we do is we change the gear macro geometry. This is a very strong recommendation that we keep mentioning in all trainings, that first focus on the macro geometry. Macro geometry means two-fight, profile shift, pressure angle, module, and so on. Only after this is optimized, start applying modifications. In the beginning, I mentioned that I don't like this tooth shape all too much. There's some slight undercut, and the specific sliding graphic here is not balanced. It confirms my gut feeling that this is not a nice gear design. What we will use now in the tab basic data, you will find that the profile shift of the pinion is 0, and the profile shift of the gear is 1.1. We are fortunate in the sense that the number of teeth of the pinion is fairly high. This is always beneficial for modification or for optimizations, because there's a lot of margin to increase, for example, the tooth height. In this case, I want to optimize the profile shift. I use the sizing function here, and the software proposes, if I want to optimize the specific sliding, means the ratio between sliding speed that generates wear divided to rolling speed that does not generate wear, I want to minimize so that the sliding component is reduced. I accept this proposal. I have a new profile shift. And if I now repeat the calculation of the geometry, if you look at the tooth form up here, you will notice the tooth form is now changed. It looks much better. And if I look at this tooth shape, it has very nice proportions. And if I look at the specific sliding, the curves are now balanced, means their extreme values are the same at the start of mesh and the end of mesh. So now I claim that I have an improved gear design. Now I have to prove that it is improved. For this, I run the contact analysis one more time to find the new amount of wear. Remember, in the first calculation, the wear was 137 micron. Now the calculation is finished for the second gear geometry with the optimized macro geometry. You can see by naked eye somehow the situation has improved. And if I look at the numerical result, I now find an amount of wear of, let's say, 95 microns compared to 137 microns before. Of course, the absolute number, 95 micron, is not what you will experience in the field, because there's a lot of assumptions done. What is, however, quite reliable and important is the relative decrease, means from 137 down to 95. This ratio you should experience also as an improvement in the field. So first step was quite successful. Now that we have optimized the gear macro geometry, in a second step, I now want to optimize the gear microgeometry. Microgeometry on gears, we use the term to describe modifications of the flank. These can either be in profile direction or in lead direction or a combination thereof. And in this example, I only apply a curved tip relief. For this, again, there is a sizing function here. I choose that I want to have a tip relief. I want to have a long profile modification. That means that the start of the modification is at the highest point of single tooth contact, or point D, depending on whether you're more familiar with the German style of gear definition or the US. And we calculate the tooth deflection and find that the recommended value for the tip relief is 37 micron. I accept this proposal. I have here now a modification defined. And if I look at the profile diagram here under graphics, geometry 2D, profile diagram of the pinion. This is what we added. We have here, starting from the root form diameter upwards, an undisturbed involute shape, and then, excuse me, starting at a certain diameter, we have a curved tip relief applied on both left and right flank. If you look at the same in the gear geometry down at the bottom left corner here, we see in gray color the original geometry, and then the thin blue line, this is the geometry with the tip relief applied. I now want to see what is the effect on the wear. I rerun the wear calculation, and since now I have a tip relief applied, the pressure distribution on the flank will be different. Therefore, my amount of wear will be different, hoping for a lower amount. Again, if you look at the graphic, we can again see by naked eye that the situation has again improved, that the amount of wear here is even less. And if I look at the number, we are down to 81 micron here in the results field. Let me repeat, the original design had a wear amount of 137 microns. This we dropped by optimization of the macro geometry to approximately 95 micron, and now by adding a micro geometry optimization, a very simple one, very quick and dirty one. There are more detailed functions to 81 micron. Total reduction of about 40% in a few minutes. Now let us say, for the sake of argument, that the flank optimization is now completed. We are happy with the flank, and we now move on to an optimization of the root. If we look at the root area here, we obviously see that the root rounding is not maximized. We could inscribe a larger radius, thereby reducing the stress level. Now, to illustrate the stress level nicely, I want to use the FEM calculation in KISSsoft. The FEM calculation in KISSsoft for the root stress works very close to the theory. Means we use a two-dimensional model, basically a spur gear, even for helical gears. Why? The reason why we want to use finite element approach for root stress is to be able to also calculate root stresses for non-standard root shapes. Because for plastic gears, the shape of the root is basically free. you can do a circular arc, you can do an elliptical shape, you can do a sharp corner, whatever. It's independent of a tool that you would use in the, say, hobbing of a metallic gear. This means that for plastic gears, but also, for example, for forged gears or sintered gears, the root stress calculation as per the gear rating standards can be inaccurate because the root shape is not matching to the root shape that is used in the theory. For this, we have under the menu calculation, we have an option, FEM of the tooth root. In this new tab, I can select that we want to calculate the root stress of the pinion. We can define what are types of boundary condition, whether we want to apply the boundary condition on the side of a sector or on the outer diameter. Typically, it is on the side. I can choose a mesh density. I can choose a stress criterion, and I choose whether it's a plane stress or plane strain model. Since we use a two-dimensional model, a flat model, I use plane strain. If I now run this calculation, let me switch on the FEM solver. I need to reconnect. We had a crash of the network just now. Now what happens is that this tooth shape that we have here for the pinion, including the tip relief, this tooth shape is exported from KISSsoft. It is sent to an FEM software, and this is where just now something went wrong because I disconnected the network. It's a freeware, it's part of KISSsoft. There it is meshed using parabolic triangular elements, and stress calculation is performed. What we receive back as a result is the root stress calculated by means of the FEM solver at 14.34 megapascal, and this we may compare to the root stress calculated as per the gear rating standard, here at 16.43 megapascal. So if you compare these two numbers, this is the deviation between the calculation as per a gear rating standard versus the calculation as per FEM method. Now, this is the stress at the 30 degrees tangent point, whereas this is the highest stress level over the whole contour of the root. If we now look at the stress distribution itself, this is the segment of teeth that we subjected to the FEM calculation. And on this segment, I may now plot stress distribution. I am hiding the FEM mesh so that we see the colors better. And I see now my stress distribution, and let me focus here in the root area. This stress level here, this red patch, this is corresponding to the 15.15 megapascal, approximately here, I guess. Let me lock this graphic. So we keep this graphic open, and we will repeat the calculation process with a new geometry and then compare the graphics. The first thing that we can optimize is, of course, we can simply increase this radius of curvature here. For this, I change the root rounding coefficient, the root radius coefficient, from 0.3 to say 0.4. And if you look down here now, and I repeat the calculation just for the geometry, we change this radius and it becomes more, it becomes bigger. Now that I have a bigger root radius, I repeat the finite element calculation of the root. And remember, before we had 15.15 megapascal as a root stress. Now the same thing is done again. This new geometry is exported to the preprocessor. There the mesh is applied. Then the mesh is subjected or sent to the solver. There the force is applied on the tooth at the highest point of single tooth contact, or point B. It is solved and we receive as a stress result 13.65 megapascal, not so satisfying reduction. This is then the disadvantage of having gears with a high number of teeth. I open the same graphic one more time in parallel. So this is the same graphic, but now for the modified geometry with the higher root rounding. Again, I'm hiding the mesh. I'm showing a stress distribution, and I use a scale from 0 to 10 megapascal. Again, zooming in into this area. And you can see that the red area here is, it's a bit difficult to zoom in, is more evenly distributed but less deep. And from a numerical value, we see a slight reduction. So overall, we are seeing a confirmation in principle. The higher the radius, the lower the stress. That's fairly obvious. But frankly, I'm a bit disappointed. It's not that much improvement. Now that we have improved the radius, but we have kept the type of curve, the trochoidal fillet, let us try another type of curve. For this, I now apply, what I want to do is I want to inscribe like an elliptical shape down here. The advantage of the elliptical shape is that it has a high radius of curvature on one side and a low radius of curvature on the other side. If I can inscribe here an elliptical shape where the radius is high near the critical point, a high radius giving a low stress concentration, I expect some improvement. To inscribe such an elliptical root shape, we need the tooth form calculation. We have now a new tab where we can modify the gear geometry in various ways. This is one of the strongest area of KISSsoft, but also one of the most difficult to use. I add an option that the root shape should now be elliptical. And let's say the elliptical shape should be starting at the diameter of about 30.6 millimeters. This is still below the active root diameter, or SAP. Means I will not provoke any meshing interferences. And let's say that in the bottom of the room, there should be still a gap or a part of the root of 0.2 millimeter width that is not affected by the elliptical shape. If I now run the calculation just for the geometry. If we look here in this graphics, let me zoom in a bit. Then the blue color was the original geometry, means a toroidal fillet that is generated. Let me show you the generating process. This is the generating process between a rack-type tool, here in green. The rack-type tool has a circular rounding at the tip, and this circular rounding, let me switch off the elliptical shape, this circular rounding at the tip of the tool generates a toroidal fillet in the root of the gear. This is what then gives here the blue shape. However, for plastic gears, I can use, say, wire erosion to create a cavity. I'm not bound to this generating process, and I can do this elliptical shape shown here in red. Now let us see how much influence or how much we gain in terms of root stress. So I repeat the FEM calculation. The FEM calculation now is based on this red 2 form. By now you know the process. Let us wait for the result to come in. And if we look at the numerical result, we see that the stress level has dropped below 12 megapascal. It was originally higher than 15, now it's below 12. That's more than 20% improvement in the same design space. And if I look at the results again, at the graphics, I again display this. I hide the mesh and I map a stress distribution, and I use the same stress scale between 0 to 10 megapascal. And if I zoom into the root, you can now see the red area is decreased in size, and the highest value has dropped from 15 in the original shape to I think it was below 12 in this modified shape. Again, you can see it doesn't take long if you know what to do. If you don't have to talk while you're doing it, you're even faster. And the advantage is you do not need to change the overall dimensions of the gear. Still, you gain 20% strength. Again, let's say for the sake of this presentation, we are happy with the result. So we have optimized the root, we have optimized the flank, and we can say that the gear geometry design is now finished. What we check as a third part of the presentation is how this plastic gear will be manufactured, or rather how the shape of the cavity of the tool will influence the shape of the resulting gear. For this, I now focus on this graphic of a single tooth, and I will show only the final tooth shape, means the tooth shape with the tip relief and the tooth shape with this elliptical modification. So let me use dark gray color for the gear, or rather the tooth shape that we want to achieve by means of injection molding, and the tool or the cavity of the tool is manufactured by wire erosion. To consider this process, again, I need to use the tooth form. And first, I define that I want to calculate what is the shape of the cavity that generates the desired gear. The difference being, once you remove the gear from the cavity, it will shrink. This means the cavity has to be larger than the desired gear. If I now assume a 2% shrinkage amount, then I find that the cavity has to have this shape shown here in pink, so that when I remove the gear and it shrinks by 2% in circumferential and in radial direction, that the final shape is as the desired gray color. To manufacture this cavity, the shape of the cavity as pink, I have to use a wire to cut this material out. The wire travels on the inside of the pink shape at a certain distance, the distance being the radius of the wire plus what is called a spark gap. In this exercise, we say that the radius plus the spark gap is 0.3 millimeter, and since the shape should be inside the pink shape, I use minus 0.3. Then the path on which the wire must travel to cut this cavity is this cyan color path. Of course, in reality, the wire diameter you would choose lower. You can see fairly quickly that probably this will be a tricky area to have the wire travel. So the wire travels on this path, and in an equidistance here, this equidistance is always 0.3 millimeter. However, if the wire is here, moving on a corner, it will generate some radius up here. This again we can calculate by now inverting this shape, not inverting, reversing. And what we find, let me choose a nice color. If the wire travels on the cyan color path, then the shape it cuts in as a cavity is the orange color shape, not the pink color shape. And finally, if the cavity has such a radius on the tip, it will generate the corresponding radius on the tooth itself. Let me calculate this. I'm making a very small mistake here, for those who know. Then I find as the final gear geometry, let me use switch color red for the, then the final gear geometry is this curved, or at least with a radius tip instead of the designed geometry with the sharp corner. Of course, the fact that I designed something with a sharp corner and therefore a higher tip radius, and now I receive something that has a radius up here, this means that the tip form diameter drops quite a bit if the designer is not aware of the influence of the cavity. This then has an effect on the contact ratio and potentially on the vibration level of the gear set. So this is one mistake that we quite often observe in customers' design. With this, we have now optimized the flank, we have optimized the route, and we have checked how the gear can be, or rather the cavity can be manufactured using a wire erosion process, and what is the effect of the cavity shape onto the tooth shape. With this, we have done our job as designer. We have optimized something, we have checked whether it can be manufactured, and finally what we need is an export for like the CAD data. Typically, you would export, say, half of a single tooth. And of course, only the final tooth shape. This is the rounding, that is the result from the rounding in the cavity. Down here we have an elliptical shape, and up here we still have a tip relief. Let me show you. This gray line is the original involute shape, then some material is removed, that's the tip relief, and finally there's a rounding applied. But what we want to use is only this final shape. This we can now export as a 2D format, or we can also generate the pinion shape in 3D, and this 3D data includes all the modifications. This means the 3D data, maybe you can see this elliptical shape. This means that the 3D data can be used as an input to a CAM software to machine solid electrodes by a 5-axis milling machine. Let me export this as well. And then I can proceed. I have here my shape as a 3D body. I can use this either in a CAD or in a CAM software as the basis for an accurate machining of the gear or the electrode. And of course the same as a 2D shape if I need a path to supply to the manufacturer of the tool. Now, when you interact with the manufacturer of the tool, be aware that you explain to the manufacturer of the tool whether you give him the cavity shape that you desire, means considering the shrinkage, or whether you give him the shape of the tooth, and then he has to design the cavity somewhat larger. What is also relevant and is that when you export the tooth form, you have to be aware that here in the tab tolerances, you choose what is the thickness, or where inside the thickness tolerance field the graphics are generated. Here with this list, by default, you choose that what you see here as graphics, as tooth shape, is in the middle of the tooth thickness tolerance field. We recommend, however, that you make sure that you go for the minimum. Yeah, be careful for the minimum, because when you produce a lot of plastic gears, the cavity will expand, it will wear. This means as time goes on, the gears that you manufacture by injection molding, their tooth thickness increases and increases and increases because the cavity experiences wear. This means that the geometry for the tooth that you use, we recommend go for the minimum tooth thickness. This means that this graphic here shows the thinnest permitted tooth inside the tooth thickness tolerance. And then you will know the first few hundred gears manufactured by injection molded have thinnest permitted teeth, and once the tool wears, the tooth thickness will increase. This gives you the longest life of the tool. With this, I want to conclude today's presentation. We have seen 4 steps. Sorry, the software presentation. We have seen 4 steps: optimization of the flank, optimization of the root, checking what is the influence of manufacturing, injection molding, and cavity design, and finally the export of the data that you can hand over to your tool maker. Let us go back to the slides for a few minutes.
Hanspeter, excuse me, just sorry for the interruption. Just some information. We apologize, but this web demonstration will probably last along with the questions and answer section slightly longer than 1 hour. So please, we appreciate if you can stay a bit longer. In case you have a meeting or in case you have to leave, please don't forget to fill out the survey. There are only 4 questions, which is important for us. And now, Hanspeter, we will continue with your presentation and then follow with the questions and answer section.
The slides that I jumped over just now are basically what we showed in the software. You can download these slides through the GoToMeeting tool. We want to inform you that we do about 15 projects per year designing plastic gears here at KISSsoft company, designing from scratch or optimizing existing ones. For example, for high temperature applications, say drives that are used in engine compartment, see top left, or for maximized strength, see bottom left. That was a project I did myself in India for a kitchen appliance thing. Or for tolerancing and low friction. On the right side, you see a water meter. The ratio of this gearbox was about 1 to 10,000. And the gearbox was driven by a small turbine in the water flow. And here, the design criterion was to have a very low amount of friction in the whole gear train so that the metering process would be accurate. Another question is, how can you verify plastic gears? Here we have to distinguish between functional test benches, means where you use the actual gear and check whether it reaches a lifetime, or test benches to determine, for example, a wear rate factor, what I mentioned earlier, or strength properties of the gears. We work together with 4 entities who have such a test bench. One is University in Ljubljana, one is the university here in Winterthur near Zurich, and one is a university in South Germany, and also in Italy, the most recent test bench designed by Mr. Longato. He provided the images for this. And what is important, that on the test bench, you have a climate control where you can define the operating environment of the gear set. You also need a very highly precise thermal camera so that you can measure the temperature of the flank, because the temperature of the gears in operation greatly affects the material resistance. So you need to have a very good control of the temperature. That's basically one of the most important things, to have a good control and monitoring of the temperature using a high-end thermographic camera. With this, it is then possible to measure wear and correlate to calculations to find the wear rate, or to measure strength property. The method to calculate strength properties from experiments is described in the VDI guideline 2736, part 4. Finally, we want to inform you that Gleason has its own plastics gear division near Rochester, near headquarters, where we have a production facility for production of small to medium batch amount for plastic gears. We are quite experienced in the design, of course. We have all the measuring and quality control equipment, either from third parties, for example, the optical systems, but of course then also our own measuring equipment, for example, gear testers. Then please have a look at our homepage. In the training sections, there are also specific trainings for fine pitch gears and plastic gears. The content of the training, of course, is much more than what we were able to show today. And finally, if you again look on our homepage into the publication sections, you will find a number of papers on plastic gears by Dr. B, Dr. Kiesling, and Dr. Pogacnik. With this, we want to conclude. Thank you for taking your time today. And now we are open to receiving your questions.
Again, thank you, Hanspeter, for this wonderful presentation. We have a lot of questions that have come in, so we will try to answer as many as we can. And Hanspeter, the first question is related to the graphics that you have shown for wear, once for the non-iterative wear calculation and once for the iterative wear calculation. Now, for the non-iterative wear calculation, we have seen that at the pitch or at the operating pitch circle, there is only rolling, so no wear is expected. So the question is, why in the iterative wear calculation, there is still wear in the area of the pitch circle?
Imagine there's no wear at the pitch point, but just left and right to it, there is wear. Then at the pitch circle, we start to have like a mountaintop. So let's say if this is the original involute, and we have, let's say here, the pitch circle. And so we have somewhere here, and theoretically nowhere at the pitch point and somewhere here. Then at this point, the stress concentration becomes so much that there will be somewhere, and inside the calculation, we then average to some extent, we average out we average the product between contact stress and sliding speed. And even though the sliding speed is 0 here, we take, what we do is basically, this is what you calculate. And then we say from here to here, take an average. So this is something that doesn't fully work properly. We have to, let me call it, cheat a bit to consider that this peak will disappear. And we cannot calculate the contact if both gears are this shape. So we do some freestyling in the mathematics there.
Okay, thank you, Hanspeter. We have received 2 questions that are related directly to material properties of plastic gears. So please excuse me if I'm not gonna pose the question exactly as you did, because I'm combining these 2. So the question is, how did we get data for SN curves of plastic gears, especially bending and stresses, which we use in the wear calculation? If often there is only data available for pitting, for root strength, but not for pitting. And combining this question with the second one, where do we enter plastic gear data in KISSsoft?
Good. There are 2 basic sources of fatigue, also even for static strength data. for the root. In the root, you also have to consider that the strength data is temperature dependent. Let me check whether this is visible here. What you see here is a group of SN curves. Let me show the root strength of the pinion only. And these curves are for 20 degrees, 40 degrees, 60 degrees, 80 degrees, 100 degrees centigrade SN curves. Means the SN curve, there's not one SN curve, but there are several SN curves as a function of temperature as well. The source for such data is either VDI guidelines 2545 that has been withdrawn a long time ago, then VDI guideline 2736, that's replacing the previous one. And then we have a number of gear material supplier, thermoplastics material suppliers, for example, Sabic, for example, Victrex, and others, who actually do such measurements using such test rigs. And based on these measurements, they generate data as a function of temperature, sometimes only for one temperature, sometimes only for static low conditions, sometimes for fatigue, and they provide us this data. With many of them, we work together, and our users may then ask us if we include the material data in their software license. We in turn have to ask the material supplier, and we have to provide the contact details so they can approach you for promotion of their raw material. So when you get the KISSsoft license, the KISSsoft software, you may not, maybe the list of material is not complete. You then have to ask us, please give us more data, and we have to write a letter or an email to those companies telling them, look, this and this customer in this and this country with the email address such and such, he wants to have your data, can you provide it? Normally they agree, and probably they will contact you trying to promote and sell their raw material.
Thank you, Hanspeter.
I forgot one aspect of the question. The strength and the wear data is independent of each other. So some supplier may provide wear and strength data, or only one of the two. Now I'm finished.
Thank you. The next question is, in your particular example, we can see that the pinion is a thermoplastic, a PA, and the gear 2 is a through-hardened steel. Now, obviously, the steel gear number 2, would cause more wear on the plastic pinion. So is it a common situation to have a plastic pinion and a steel counter gear?
No. This is when I prepared the example, I had exactly the same comment from one colleague that normally it should be the other way around. The reason why I used it like this is, if we made the plastic gear with a plastic pinion with a steel gear, the resulting wear curves look more smooth. That's just something we found. If I were to do this exercise with a different material combination, a more realistic material combination, the results would not look so pleasing to the eye. And one purpose of such a demonstration is to show you something nice.
And please your eyes.
The answer, yes. The answer is this is not common. If it's the other way around. But for the purpose of the presentation, I tweaked the whole calculations such that they run fairly quickly and that the results underpin our statements.
Thank you, Hanspeter. I still see that most of the participants are still online, so if you don't mind, let us continue with the question and answer section. Is that okay for you?
Yeah.
So the next question is, would you recommend tooth flank modifications for plastic gears, even if the modification amount is less than the tolerance band of the injection molded parts?
Yeah, that's a tricky question. That's always the same discussion that we have. I believe yes, because let me show you an example. In this example here, let me make this amount smaller. Let's say I have 12 microns tip relief, and so I have a modification. Let me use 10 so that we have an order of magnitude. So I have 10 microns modification, and I included in the graphic a tolerance band. This tolerance band is at the moment 60 microns wide. And the modification itself is only 10 microns, so less. Still, if you assume, and that's a big if you assume that your manufacturing errors are random, then the mean manufacturing error is 0. Again, if you assume random errors over the thousands of plastic gears you manufacture, the average error is 0. This means you will see a shift in the manufactured gears towards a 10 micron tip relief. You may have gears that are 10 microns. Sorry, let me explain first. You have a 13 micron distance here inside the tolerance field. You target 10. This means you will end up on average with 10 plus minus 13 divided by 2 is 6.5. So if you manufacture 10,000 gears, the worst one will have, or the one with the lowest tip relief will have a tip relief of 10 minus 6.5, that is 3.5. And the one with the biggest tip relief will have 10 plus 6.5, 16.5. Still, in average, most of them will be near 10 microns if you think of a normal distribution. So if you say that this range from 10 to 26 micron, let's say this constitutes a 6 sigma range, means plus 3 times standard deviation on one side, minus 3 times standard deviation on the other side. Then you will see, for example, that if then in one standard deviation is 26 minus 10 divided by 6. So 26 minus 10, that's the, so I made a mistake. Why did I say 13? I should have said 16, sorry. So the range is 16. Let's say this is 6 sigma, so divided by 6. So the standard deviation is 2.6666 times 2. Then, so this is 2 sigma range plus minus 1 sigma. Then you know that approximately 2/3 of all gears that you manufacture will have a tip relief of 10 minus 5.3 to 10 plus 5.3. So approximately 2/3 of all gears manufactured will have a tip relief between 5 to 15 microns. So basically you just shift the mean value, provided that you have a random manufacturing error.
Thank you, Hanspeter.
So the answer is yes.
Yeah. The next question. How do you take into account internal heat flux due to polymer material internal friction material hysteresis while meshing. How much tooth high-speed oscillations can influence the temperature rise?
Very simple answer. We don't consider, and I don't know. I know the concept. You have the hysteresis, you generate heat inside the gear, but we don't know how to consider. Sorry.
Thank you. If using plastic gears, how is the draft incorporated in the design? Is any draft needed in the tooth area? If yes, where is the parting line typically, and what draft angle value is acceptable? It's difficult questions coming in.
Yeah. Okay. Here I have to answer in two parts. The practical side, like how much draft angle you need, and where is the parting line, I cannot answer because we simply don't have the practical experience on making tools and manufacturing plastic gears here in Switzerland, or me. I can forward the question to Gleason Plastics, however. From the software side, the way you can consider a draft is by means of a helix angle modification. Let me close a few windows here. And here as a modification, let's say on the pinion, I define a tapered helix angle modification. Let me show you. So I choose a tapered helix angle modification, and let me use a very high value so that you will see something, and seeing is believing. What I did now is I applied a 25 micron draft per flank. If I look at this in the tooth trace diagram, this is now looking from the top land side. You can see that here on side 2, I have reduced the tooth thickness by 2 times 25 micron. On side 1, I have the original tooth thickness. So you would pull out the gear from the cavity downwards. Now this draft angle is then also represented in the 3D graphics. I hope it's visible. No, let me increase the value. I'm trying 150 microns. Okay, now you can see it very clearly. I was quite lucky with the number. You can see now the draft angle on this side. I have reduced the tooth thickness so that it's almost 0. You can see very narrow top plan. And on this side, it is the original value. If I do the draft angle on one gear only, and then look at the contact stress, means at the contact stress, of course I will have more stress on this side, because here the tooth is more into the mesh. Sorry, that's the wrong calculation. I have to run the contact analysis. So if I apply a draft angle on one gear, I influence the lead-wise load distribution, of course. Let me show you this on the flank. This is too much draft angle for the contact analysis. Let me reduce it.
Maybe meanwhile, while it's calculating, can I ask you next question? So there are two questions which go the same direction. Will tooth contact analysis sometimes be available also for crossed helical gears? And the second question is this calculation applicable to worm gears?
For cross-axis helical gears, it's on the roadmap that we developed this. At the moment, we don't have it. The main difficulty there is that the tooth stiffness theory is virtually non-existent. And for worm gears, for the enveloping worm gears, like what you typically have in an industrial environment, honest answer is it will. If we do it, it will take a long time. So at the moment, probably no. Why is this not working?
Okay, so let me then ask you one final question, and then we will finish for today. So how can we obtain zero backlash, so no gap gear meshing, in high stiffness plastic versus steel gears meshing, considering high temperature expanding, for example, of PEEK? Yeah. Is the question clear, Hanspeter? Should I repeat it?
Yeah, no, just trying to run this. If you have a fairly high temperature plastic gear that is stiff in high temperature and you want to achieve zero backlash, then you have to pre-tension the mechanism. If you want to have exactly zero backlash. If you allow for a small backlash, then you have to use what is called here. Let me finish this first on the draft angle. So we apply a draft angle, and the reason why it didn't work is because I had the wear iteration still. If you apply a draft angle, then of course the load distribution is not good anymore. And of course, as I mentioned before, if I have here on this side of the tooth a higher tooth thickness compared to here, more load will be transmitted on this side. If you have the opposite draft angle on the mating gear, then these two effects cancel each other out. But you have to make sure that the gears are then assembled with the right side towards each other. This means if you have a symmetrical design of the gear body, then sometimes you have the draft angles working against each other, and sometimes they help each other. And I don't like this. So if you have draft angles applied, try to make them such, or the design such, that after assembling the gear set, the two draft angles compensate each other. That's the best solution. Otherwise, you have an uneven load distribution from the left side to the right side. Now back to the question of the no backlash condition. Zero backlash under all operating conditions is practically only possible with a pre-tension system. This means a variable center distance where you apply, for example, a spring force, or yeah, that's the most economical solution. Or that you have a non-constant tooth thickness on one gear and you push it sideways. That's also a design solution. To minimize the backlash in operation, you have here the operating backlash calculation, where you can play with temperatures, moisture absorption, and so on to achieve a zero backlash in one condition, for example, highest tooth thickness tolerance at lowest center distance tolerance and highest temperature. That's the condition where the backlash is minimized. You can then calculate it such that it is zero in this condition. And then at the lowest temperature, highest center distance tolerance, and lowest tooth thickness tolerance, you then end up with a given amount of backlash that you can only reduce if you narrow down all tolerances. Another influence is if you use fiber reinforced plastic gears like glass fiber or carbon fiber, the thermal expansion of the plastic gears is reduced. This means that the change of the backlash, if you reduce the temperature or increase the temperature, is less. That then allows you to target a lower total backlash.
Okay.
That's one of the topics that takes about 2 hours in the training, this operating backlash calculation.
I'm a bit surprised, Hanspeter. We still have most of the people online. That means the questions are important. So I will take my freedom and ask you 2 final ones, and then we finish because they just came in recently. So is if the shrinkage does not have an exact pattern as we have in the tooth form calculation, how can we control the micro modifications? And a question related to that is, what Dean class of gears are physically achievable for plastic gears? Maybe I think we can combine these two questions.
Yeah. Let me answer the second question. The Dean quality grade that can practically be achieved. The best companies we know are at grade 5. That's quite tough. So Dean 5 is, we know companies who can do it, but that's not common. The first part of the question, how to consider that the tooth thickness changes with diameter, or the deviation of the tooth thickness changes with diameter. This is a function that we will have in the next release. Let me give you a preview. Now I'm flying solo. I have to try. This is an internal software version, and what you can do in the next release, let me increase the size. And change the language. In the next version of KISSsoft here in the tab modifications, there will be a function here that you can import a measurement grid. Means you manufacture a first batch of plastic gears, do a tactile measurement, and import the measured coordinates of the flank. Then you have the true geometry in KISSsoft. That is one approach. If you don't manufacture if you do not do a first batch of manufacturing first, you can modify the tooth form, say in a CAD system, if you know what is the shrinkage in each direction, and import the tooth form using the tooth form calculation and import it as a DXF file. Where is it? Here, import cylindrical gear data. And then you can import directly a DXF file of a shape. Means, let's say the designed gear is a pure involute of a certain tooth thickness, and you know from experience that, say, at the base of the tooth, you have a deviation in thickness by that much. At the middle of the tooth, a deviation in the thickness by this much, and at the tip of the tooth, a deviation in tooth thickness direction, again by another value. You can then export the DXF file of the designed geometry from KISSsoft to a CAD system, change in the CAD system as you want, and re-import it back from the CAD system to KISSsoft.
Okay,
basically, the basic idea is in KISSsoft, the gear geometry can be calculated or measured or from a CAD. That's the thing.
Thank you so much, Hanspeter. And to honor our students, a question from a student from Czech Republic University. The student is building up a test rig for 3D printed plastic gears, and he's concerned because of the speeds of the test rigs will cause a failure due to temperature of the 3D printed plastic gears. So his question is, can you give any advice, for example, maybe with the calculation of scuffing in KISSsoft to somehow predict the thermal rating of such 3D printed gears?
Don't use the scuffing, use the contact analysis. So you have here in the contact analysis, when you run the contact analysis, we also calculate the friction energy. So from the contact pressure between the flanks and the traveling speed and an approximate friction value, you will then find here in the result what is the heat generated per revolution. Where is it? Here. And if you go to graphics, contact analysis, efficiency, if you look at the power loss, that doesn't help much. If you look at heat here, heat on the two flank and where is it? Okay, this is a bad example because I have a lot of modifications and I played with the draft angle. Here you can see the draft angle and here you can see numerical problem. But this graphic shows what is the heat generated over the path of action expressed in joules. You can then, as a function of the torque, and as a function of the torque, you then get the result of the heat generated, and to some extent you may be able to estimate whether this heat can be removed or not. So this is similar to the scuffing calculation, that on one side the heat from the friction is generated, and the heat is then compared for the scuffing with the lubricant properties, and in your case with the thermal resistance. The cooling calculation will be tricky. That is not part of KISSsoft.
Thank you, Hanspeter. So I think we're finished. Once everybody closes the tool, there will be a small survey, and especially question number 4 is very important. What do you expect, or what would you like to have as topic for the next web demonstration? As you see, the format of this web demo was slightly different. We received your input and we tried to be more inside the software. So please let us know if you're happy with it. And otherwise, me and Hanspeter, we would like to wish you a happy day. And thank you so much for your participation and all your questions.
Yeah, thank you, ladies and gentlemen. It was a pleasure talking to you. Bye-bye.
Bye-bye.